Hello. In this lesson, we're going to talk about the operations of functions. What do I mean by operations of functions? In last week, we talked about functions and inverse functions. And we can see they're all, we have covered all 8 functions and their domain and range and related concepts, right? By saying operational functions, we mean that if there are 2 functions, right? First of all, we know function is a rule, right? We know a function is a rule. What kind of rule is it, right? There's input, and the rule is a function. It produces an output, f of x, right? Then how about there are 2 functions? What if there are 2 functions? Suppose there are 2 functions. There's another function we call g. Okay, and g is a rule as well. A function is a rule, right? It assigns each element in domain exactly 1 element in the range. So there are 2 functions. So we have 2 rules, right? We have 2 rules. And what can we do about these 2 rules? Well, we can add these rules. We can add, okay? And we can subtract. Okay, so let me make a table about what the operations we can do with functions. We can add these 2 rules. And we can also subtract these 2 rules. And we can multiply these 2 rules. And we can divide these 2 rules. And what is more, there's another operation which is going to be relatively new. Composition. So before we look at the composition, let's look at each one of the rules, right? The rule of addition of 2 functions, we basically take an input and give it to the sum of the function. So one rule adds another. So one rule adds another. So the sum of these 2 functions becomes a new rule. And it still produces exactly 1 output. It's called f plus g of x. Right? Let's look at the notation. Let's look at the notation. And I believe you guys have learned about these rules before. So we can have the sum of functions. And of course, we also can have subtraction of the functions, right? So if the rule becomes f minus g, right? So there's an input, it produces exactly 1 output. So that will be subtraction of 2 functions. So from addition becomes subtraction, right? So these are adding, subtracting of 2 functions. Then how about multiplication, division of 2 functions? There you go. Okay, so I'm going to continue this journey here, right? I'm going to put this the last. Okay, they're all important. For multiplication of 2 functions, it is defined 1 function multiply another one. So f times g, right? It forms a new rule. It still takes input. It produces an output. So the output will be f times g of x, which is defined as f of x times g of x, okay? Quotient, right? For quotient, it's another rule. So one rule divided by another rule, and it's on function. Okay, so this will be a new rule. This will be a new rule. For this new rule, it takes input, okay, and it produces an output. It produces an output. So this is how we write it. We're going to have an example. Okay, so this is defined as f of x over g of x. Okay, but we must make sure the denominator cannot be 0, right? We always make sure that those basic assumptions are being satisfied. I believe these operations are pretty familiar to all of you. And I'm just going to give you an example, okay? Give you an example to cover these 4 operations. And then we're going to talk about composition of functions. Okay, so adding, subtracting, multiplying, dividing, or functions. Suppose I have a one function that's f, right? So this function is f of x. Suppose I take this function. And the g function, I'm going to take it to be 1 over x, right? So if the f plus g, it's going to be a new rule, right? So f plus g is going to be a new function. It's going to be a new function. Okay, so that's going to be f of x plus g of x. So that's going to be x plus 1 over x, right? It produces a new function, and you can make it more complicated if you wish, right? Another operation that's often used, but I think I didn't mention earlier, is you just multiply a function by a constant. Okay, multiply by a function by a constant, but that can be actually made from the special cases, right? So let me put that as another category, right? So if you multiply a function by a constant multiply a function, say c times f, right? That makes a new rule as well, right? So c times f of a function is defined as the constant multiply f of x. Okay. One of the concern would be, what would be the domain and range? Well, the domain would have to be the common part of these 2 functions, right? Will have to be the common part of these functions. For example, in this case, f of x, the domain is all real numbers, right? This domain is all real numbers. That's all real numbers from negative infinity to positive infinity. But the latter function, the domain is x cannot be 0, right? So when we put them together, we have to make sure both functions can be operated meaningfully. And therefore, the final function, which is the sum of the function, that domain is going to be x is not equals to 0. Okay, by the same way, we can work with the difference of a function f of x subtracting, right? Subtracting, right? And the domain will be the same, right? Multiplication, okay, multiplying these 2 functions. And here we need to be a little bit careful, okay? F of x here is x. okay, multiply 1 over x. And you may say, hey, we can cross them out. We can cross out the x. Yes, we can. We get 1. But we also need to understand the reason we can write them down this way because x cannot be 0. Otherwise, you cannot apply 1 over x. Therefore, in this case, the domain is still x cannot be 0. Okay, because that's required for such an operation to carry it out. Okay, last one, quotient. Okay, so in this example, when we look at the quotient of these two functions, then we will have f of x, right? That's x. That's x in the numerator, 1 over x, that's g. And of course, provided that x cannot be 0. And so in the end, x divided by 1 over x, okay, domain x cannot be 0, right? X cannot be 0. Make sure that, the operations are meaningful. Excuse me. And in this case, how do we simplify that, right? Simplify this complex functions. We multiply by 1. And this 1 we're going to choose to be the common denominator of a numerator and denominator, which is going to be x over x. And x times x, that's going to be x squared. X times 1 over x, that's going to be 1. So we will end up with x squared over 1, which is also x squared, right? You can see we have any two functions. Then we operate them by adding, subtracting, multiplying them, or multiply by a constant. Then we will get a new function. And the domain of the new functions, right? Domain of these functions, we have to make sure that both domains, the common part of the two domains. All right. I believe this is not familiar. This is not new to you, so I'm not going to give you more examples. And we're going to move ahead to talk about the composition of functions. Composition of functions. What kind of operation is this? What kind of operation is this? Okay. This kind of operation, okay, what does it mean? Okay, this is what it means. What f is a function, g is a function. Okay, so f is a function. That means f is a rule, right? F, g are functions, respectively. They each have their own domain and range. They each have their own domain and range. But how is f, composite g means? Well, it takes on an input, it produces an output. But how does it produce that output, right? This is how it's been defined. So f of, listen to how I pronounce and how I read the process. F of g of x, f of g of x. So what is the process, right? I'm going to call it the flow. I'm going to call it the flow. Okay, there's a certain order. There's a certain order. So the output or the input is x. The input is x. X is first given to the rule of g. It produces an output called g of x. Okay, then g of x will serve as an input, and this input will be the input for the rule of f. And then it produces f of g of x. So this process is called a composition of function. And you can see that typically x has to be in the domain X has to be in the domain of what? It has to be in the domain of G, right? And G of X, right? G of X is going to be where? Is going to be in the domain of, in the range, okay? In the range of G, but in the domain of F. So G of X is in domain of what? Domain of F. Okay. Input is from the domain of G, and the output in the range of G or in the domain of F. So in the end, it will fall into F of G of X is going to fall into the range of F. Okay, so this is the process. This is the process. Okay, let's take some examples. Let's take some examples. Let's take some examples. Okay, so now I'm going to have two functions. F function, I'm going to make it x squared. Okay, and G function, I'm going to make it square cubic root of X. Okay, be aware of their domain. Okay, I can do F composite G. F composite G. Okay, what do I get? I'll get F of G of X, right? That's the definition. So what does it do? Suppose if when I do F of G of X, and that's going to be from the input of G, right? What's the input of G? All real numbers, right? So X is from all real numbers. It can be any real numbers. Okay, so that's the process. All right. And given to the rule of G, the rule of G. The rule of G is taking a cubic root. It's taking a cubic root. That's a G of X. Okay, that's a G of X. And then this G of X is going to be given to what? To F. So the rule of F applies. What is the domain? Does this fall in the domain of F? What's the domain of F? Domain of F is all real numbers. Domain of F is all real numbers. So this is from all real numbers. So we ended up in all real numbers. And then we apply the rule of F, and we're going to square the input. So this input is going to be squared. That's it, right? And the domain for the final function, which we get, right? Which is if we continue to operate this, okay, F of G of X is going to be F of G of X. G of X is a cubic root of X, right? And then we apply the rule of F. So we will end up with cubic root of X squared, cubic root of X squared. Okay, so this is the new function. And that's the consequence of a composition of functions. And you can do G composite F if you want to, right? You can do G composite F, F composite F, G composite G, right? So say let's see what do we do? What if we do F composite F? Okay, I'm sure you guys have learned this before. It just so f composite f, so that will be f of x, right? F of x. And what is this process, right? You have input, give it to f, given the rule of f, it produces an output. Oops. It produces an output, which is f of x. In this case, f of x is an x squared. Okay, x squared will serve as input for f one more time, because that's going to be f again. It produces, the input is being squared. So this is the input. Input being squared, and that's going to be x raised to the power of 4. You see that? Okay, so composition will produce new functions, continue to produce new functions, and you get more and more. You can get a very complicated functions by composition. And next, okay, we really want to focus on is that last week, right? Last time we talked about inverse functions, right? We talk about inverse functions. Inverse function, we have f, right? So that's another function. Another important example we're going to talk about. Composition of inverse functions, okay? Composition of inverse functions. Okay, composition of inverse functions. What we mean by, so last time we talked about f of x equals x raised to the power 3, right? And we have also found its inverse is cubic root of x, right? We talk about their domain and range. Their domain and range are the same, right? And we did the graph. So let me make the fonts a little bit larger so you can see the negative sign on the shoulder. Okay, we did the graph, right? We recap the graph. Okay, recap the graph. The graph we did, right? We graphed both functions, right? So we're gonna put the graph together again, right? F of x, which is, right? It's pretty familiar to us. That's the function. Okay, so let me just bring this, just make some adjustment of the, let's see, say negative 5. I'm just making some adjustment. So here I'm gonna have negative 5 and 5 to see if that works, right? So this is a cubic function. This is a cube function, right? X raised to the power 3. And then we're going to put in the x raised to the power, the root of 3, right? We did these two functions in the previous lessons. Okay, so let's add the inverse, right? We have a different color for the inverse. Let's make it red, right? The inverse function. And we noticed, right? We've done a few pairs of inverse functions that are, two pairs of inverse functions, function and its inverse, right? And we know there's a common feature. They are symmetrical along this line, y equals to x, right? So we knew that. We've done that, right? So just to make sure you understand what I'm talking about, this one, right? this is x raised to the power 3. Okay, this is raised to the power 3. And this other one is root 3. Okay, these are the functions that are inverse to each other. Okay, and this one is y equals to x. We talk about that this is the common feature for any pair of function and its inverse, if they're one-to-one function. Okay, so if for any pair of one-to-one function, they all have these kind of symmetrical features if you graph them. Okay, they're symmetrical along the line of symmetry, a line of symmetry. Now, next, okay, so after we review this, how about their composition? How about their composition? Right, we just talked about composition. How about their composition? What happened to their composition? Well, here we go. Right? What we want to analyze is F composite its inverse. And the other one we want to see is F inverse composite F, right? F composite G composite F. But here, the two functions in composition are inverse functions to each other, okay? So inverse functions to each other. Inverse functions to each other. What will happen? What will happen? Okay, so let's see how we would do it. How we do it. For this first composition, right? Of course, we have to consider domain, right? It is going to be F of F inverse of X. And that's the definition. In other words, we take a number from the domain of F inverse, okay, from the domain of F inverse. Domain of F inverse here, x raised to the power root of x, root 3 of x, that's all real numbers. So this x is from all real numbers, okay, from the domain of F inverse, all real numbers. Okay, and it comes out, right? Because the F inverse applies, so we have a root 3. Oops. Cubic root of x. That's the rule function. And now the range of this is all real numbers, and this is also in the domain of F, because next we're going to give it to the rule of F, right? According to this composition. And the rule of F says I'm going to take your input and take it, and then I'm going to power it by 3. We're going to power it by 3. So whatever input you give me, I'm going to power it by 3. And what does this equal to? This equals to x. This equals to x. Okay, so what do we see here? So what do we see here? Okay, on both operation, F of F inverse, that's a cubic root of x. And then we power by 3, right here. And the final answer is x. Now, let's look at the other composition. Let's look at the other composition. The other composition, okay, is defined as F inverse of F of x. Okay, the flow is x will be the input for F. So the first rule that applied here is the F Okay, what is f? F is power x by 3, power x by 3. And the domain of x raised to the power 3 is all real numbers. So once more, the domain is all real numbers. Domain is all real numbers. It produces an output which is powered the input by 3. And then this fall into the domain of the cubic root, right? So we can apply the rule of F inverse. So we're applying the rule of F inverse. And after that, F inverse rule says whatever input you give me, I'm going to take a cubic root of your input. And what does that equal to? It equals to x again. It equals to x again. Ha. Okay. If we look at the function operation, right? Most of the time you're going to do this kind of operation instead of the flow. I'm doing the flow sometimes just to give you a sense of process and order of operation. Order of operation is you operate it from inside out. We operate it from inside out. So F inverse, right? F inverse. So we take this operation. So we apply the rule of F first. The rule of F is power the input by 3. So we get that. And then we we apply the rule of cubic root. So we ended up with a cubic root of x to the power 3. And we end up with x. All right. So let's summarize this. This equals to x. All right. And the other one is also equals to x. Okay, for this particular pair of function and one-to-one function and its inverse. Even though these two are written this way, order matters. Okay, order matters. Now the question is this true only for this pair of a one-to-one function and its inverse, or it is always true? The answer is it is always true. Okay, this property is always true. Okay, actually I don't need to use always, right? But always is to emphasize, because mathematical truth, once true, is always true. It's true for any pair of one-to-one function and its inverse. So this property, okay, so these two properties, okay, this properties, always true, okay? Why do I emphasize this property now? Because we're going to be using it a lot. We're going to be using this a lot throughout the semester, okay? So this is one of the most important one-to-one function properties. So summarize, so let's summarize, right? We have talked about the operation of the functions, adding, subtracting, multiplying, dividing. And then we made a composition of functions, right? We made a composition of functions. And then we observed the composition of one-to-one functions and its inverse, right? Of course, these one-to-one functions, they're both one-to-one with each specified domain and range. And they not only have this feature, right? Symmetrical along the line of y equals to x, And analytically, they also have this particular property. And this property is true for any pair of one-to-one functions and its inverse. We know the inverse. Once we have it, it's unique. Okay, once we have it, it's unique. And now let's look at the functions we have covered before. Right? Look at the functions we have covered before. Among the functions we have covered before, right? We just discussed these two functions. They are inverse to each other. They're inverse to each other, right? And did we discuss other functions that are inverse functions to each other? Well, this function, its inverse is the same as itself. Okay, that will also be true. That will also be true. Okay, this function, the inverse function, is itself. These two functions are not inverse to each other, but we can create one for, we can create that inverse function for this guy. For example, the inverse function for this guy, we talked about this, right? We talked about this. So as your, as for your study, right, after class, okay, if we put a constraint on the domain of this function, and they're inverse to each other, we talk about this. We talk about this, right? So what do we have? So this function, right, its inverse is x squared, the red, right? Let me remove that other red. Okay, so these are inverse function to each other as well. It is symmetrical along the line of y equals to x, the green. The green and broken. So for this pair, if you, right, so you can call this the inverse. Okay, so let me write 175%, make it larger. So another pair of one-to-one function and its inverse. Okay, we studied this. If you didn't watch the previous one, please go back to the previous week, right? How we have created that. Of course, this function I have to make adjustment. Okay, hold on. I need to make some adjustment. So this is 0, and that should do. Okay, hold on. Okay, sorry. That's a 0. All right. So these two functions are inverse to each other because I made an adjustment to the domain, right? So only half of it. And these two functions are inverse to each other. And you can also apply function and its inverse as we did in, in the example we just did, similar. So this, let's make this your homework. Let's make this your homework, right? So for any pair of one-to-one function and its inverse, right? That's our final conclusion, okay? Which with this very important property, we will see this property being used over and over again for exponential functions and their inverse, trig functions and the inverse trig functions, and they're being played out over and over again. Okay, and that's the reason we introduced this idea right here, right now. So thank you for watching. That's all for today. I will see you guys next time. Thank you for watching.